Quantum algorithms implementation challenges. The landscape of quantum computing is rapidly evolving, yet its practical implementation remains fraught with challenges that hinder widespread adoption. Quantum algorithms, which promise exponential speedups over classical counterparts in domains such as cryptography, optimization, and machine learning, are still largely confined to theoretical models and laboratory environments. This article delves into these complexities, exploring not only the technical hurdles but also the broader implications for developers and researchers aiming to harness the power of quantum computation. As we navigate through the intricacies of implementing quantum algorithms, it's essential to recognize that each challenge is interconnected, influencing everything from hardware design to software development. Understanding these multifaceted issues provides insight into why progress has been slow despite significant investment in research and development across various institutions worldwide. Fundamental limitations of current hardware. One of the most pressing issues facing the realization of effective quantum algorithms lies within the limitations of current quantum hardware. Unlike classical computers, which rely on stable bits, either 0 or 1, quantum systems utilize qubits, entities capable of existing in superpositions of both states simultaneously. However, maintaining coherence and minimizing decoherence remain critical obstacles that impede reliable computations. Decoherence occurs when qubits interact with their environment, leading to loss of information and errors in calculations. These interactions can be caused by factors ranging from thermal fluctuations to electromagnetic interference, making the creation of error-free quantum circuits an arduous task. Researchers have devised techniques such as dynamic decoupling and error correction codes to mitigate these effects, yet they often come at the expense of computational efficiency. Coherence time, a measure indicating how long a qubit maintains its state before interacting with external influences. Shorter times necessitate faster operations. Error rates, even minor inaccuracies during gate operations, accumulate exponentially, requiring sophisticated error correction strategies that increase resource requirements significantly. Algorithm design complexities. Designing efficient quantum algorithms presents another formidable barrier due to the fundamentally different nature of quantum mechanics compared to classical logic gates. Traditional algorithmic paradigms do not always translate seamlessly onto quantum platforms where entanglement and superposition govern behavior. As a result, developing novel approaches tailored specifically for quantum architectures becomes imperative. This divergence means that conventional problem-solving methods must undergo substantial rethinking. For instance, while classical algorithms might optimize pathfinding using graph traversal techniques, quantum versions could leverage Grover's search or Shor's factorization method instead, offering potentially dramatic improvements under certain conditions. Entanglement utilization. Effective utilization of entangled particles forms a cornerstone of many powerful quantum algorithms. Entanglement allows qubits to share states instantaneously regardless of distance, a property known as non-locality, which enables parallel processing capabilities unattainable classically. However, creating and sustaining high-quality entanglement across multiple qubits proves challenging. Current experimental setups face difficulties achieving sufficient fidelity in generating multi-qubit entangled states without inducing unwanted noise or degradation. Techniques like photonic linking and ion trap arrays offer promising avenues but require precise control mechanisms that are technically demanding and costly to implement at scale. Scalability issues in quantum systems. Scaling up quantum systems beyond small prototypes poses considerable engineering difficulties. While individual components may function well independently, integrating them into larger networks introduces new layers of complexity related to interconnectivity and synchronization. Ensuring consistent performance across expanded configurations demands innovative solutions. The physical layout plays a crucial role here. Whether utilizing superconducting circuits, trapped ions, or topological qubits, each technology brings distinct advantages alongside unique scalability constraints. Superconductors demand extremely low temperatures, whereas ion traps require vacuum chambers, an aspect complicating integration efforts further. Cryogenic requirements, Many quantum processors operate near absolute zero, minus 273 degrees Celsius. To maintain stability, cooling infrastructure adds cost and maintenance overheads. Vacuum chambers. Trapped ion implementations need high vacuum environments, limiting mobility and increasing system fragility against environmental disturbances. Software development constraints. Developing robust software ecosystems compatible with emerging quantum technologies represents another hurdle. Classical programming languages lack direct support for quantum phenomena, forcing developers either to use specialized tools or manually simulate behaviors, both options being suboptimal for real-world applications. Languages like Q#, Python-based frameworks such as Cirq, and others provide abstractions facilitating easier interaction with quantum hardware. Nevertheless, debugging and testing processes differ markedly from traditional workflows, presenting steep learning curves even for experienced programmers accustomed to classical paradigms. Simulation versus real execution. Simulating quantum algorithms on classical machines offers limited utility given inherent limitations in processing power and memory capacity. Though useful for initial prototyping phases, simulated results rarely reflect true behavior encountered during actual execution due to approximation errors introduced by classical simulations. Moreover, simulators cannot fully replicate characteristics like decoherence rates or measurement uncertainties present in genuine quantum devices. Thus, relying solely on simulation hampers accurate prediction of runtime performance metrics necessary for optimizing code effectively beforehand. Interdisciplinary collaboration needs successfully overcoming implementation barriers requires collaboration spanning diverse fields including physics, computer science, mathematics, and material science. Isolated expertise limits innovation potential since breakthroughs typically arise from cross-pollination among disciplines rather than singular domain knowledge alone. Institutes focusing exclusively on theoretical aspects often struggle translating findings into tangible products without input from engineers familiar with fabrication techniques or physicists versed in material properties affecting device reliability. Establishing channels fostering such interdisciplinary dialogue remains vital for accelerating progress toward viable commercial solutions. Material science contributions. Discoveries regarding better insulators or conductive materials enhance chip designs enabling longer coherence periods. Computer architecture insights. Lessons learned from classical architecture inform optimal layouts, reducing crosstalk and improving signal integrity in quantum circuits. Economic barriers hindering adoption. High costs associated with building and operating quantum computers represent another impediment, preventing broad industry engagement. Fabrication facilities equipped to handle nanoscale precision required for producing functional qubits involve massive capital investments far exceeding those typical for silicon-based manufacturing units. Additionally, ongoing operational expenses, including energy consumption for cryogenics, routine calibration checks, and replacement parts, are prohibitively expensive for most organizations outside elite academic labs or government agencies funded specifically for cutting-edge R&D initiatives. Such financial burdens discourage private sector involvement unless clear ROI pathways exist soon. Cost-benefit analysis dilemma. Conducting thorough cost-benefit analyses proving viability of transitioning towards full-scale deployment remains complicated. Potential gains promised by quantum advantage scenarios often depend heavily upon future technological advancements whose timelines remain uncertain. Investors seeking immediate returns find themselves hesitant investing heavily upfront without assurance that projected benefits will materialize predictably within acceptable risk parameters. Consequently, funding flows tend concentrated around few pioneering entities rather than distributed widely enough to spur competitive ecosystem growth, beneficially impacting overall field advancement pace. Regulatory frameworks and ethical considerations. Emerging regulatory landscapes surrounding data privacy laws complicate matters further, especially concerning cryptographic security assurances provided via post-quantum encryption, standards currently under evaluation globally. Governments keen on safeguarding national interests increasingly scrutinize developments closely, ensuring any implemented protocols meet stringent compliance criteria before public rollout. Furthermore, ethical dilemmas emerge, particularly regarding access controls. Who gets privileged early access? How transparent should proprietary methodologies remain? Addressing these questions proactively ensures responsible usage patterns aligning with societal expectations, promoting trustworthiness essential for long-term acceptance of transformative technologies. Data privacy laws. Compliance mandates rigorous audits verifying adherence to international norms governing sensitive information handling practices. Ethical access control. Balancing openness versus exclusivity fosters inclusive innovation while protecting intellectual property rights, fairly distributing rewards proportionally according to contributions made. Education and workforce preparation. Preparing a skilled workforce adept at navigating complexities inherent in quantum algorithm development constitutes another key consideration. Educational programs must evolve swiftly, incorporating hands-on experiences involving real quantum hardware alongside theoretical instruction covering fundamental principles underlying quantum mechanics. Universities partnering with tech firms establish joint curricula blending academia with industrial needs, ensuring graduates possess relevant skills matching employer expectations accurately. Such collaborations bridge gaps identified frequently when fresh hires demonstrate inadequate familiarity working directly with quantum systems deployed commercially already. Curriculum evolution necessities. Integrating quantum computing modules into existing STEM courses demands careful curriculum redesign reflecting rapid changes occurring continuously within the field itself. Faculty members engaged actively in research benefit immensely from staying updated regularly, attending conferences, workshops, enhancing pedagogical effectiveness dramatically. Online resources complement classroom teaching substantially, allowing flexible self-paced study options accessible remotely anywhere, anytime, convenient, empowering learners pursuing careers irrespective geographical restrictions imposing limitations traditionally faced previously, attempting entry-level positions lacking formal qualifications initially. Potential future developments. Despite numerous challenges outlined above, optimism persists regarding eventual success stories emerging once foundational problems get resolved satisfactorily. Innovations targeting improved qubit reliability coupled with enhanced error correction schemes likely pave way forward, eventually rendering today's experimental models obsolete, replaced entirely by scalable fault-tolerant architectures ready for mainstream application purposes. Advancements anticipated include hybrid models combining classical digital cores with quantum accelerators executing selected tasks efficiently, thereby leveraging strengths mutually reinforcing outcomes favorably. Additionally, cloud-based services providing remote access simplify experimentation, lowering entry barriers considerably, encouraging wider participation, driving accelerated discovery cycles benefiting entire scientific community collectively. Conclusion. Implementing quantum algorithms faces myriad intertwined challenges stemming from hardware limitations, complex algorithm design necessities, scaling difficulties, software compatibility concerns, economic deterrence, regulatory scrutiny, educational prerequisites, and ethical considerations alike. Overcoming these requires concerted multidisciplinary effort, embracing collaborative spirit, transcending disciplinary silos, facilitating holistic solutions, addressing root causes comprehensively. For practitioners involved deeply immersed in algorithmic exploration pursuits, keeping abreast latest advances remains paramount endeavor, ensuring readiness, adapting dynamically amidst ever-changing terrain, characterizing nascent stages, transformational journeys unfolding ahead, eagerly awaited by global audiences, keenly observing milestones achieved, progressively shaping tomorrow's technological reality positively.